So welcome everyone to the third edition of this seminar for this semester. And today we have two interesting talks which will be presented from Lucas a bit later. But before that, I want to point out again that you can use the Q&A button from Zoom to ask your questions. You can also ask them anonymously, so we can have a discussion round after every talk. And so without further ado, I would say I would give the word to Lucas so we can start with our first talk.
Thank you very much. I would say Heiko would be probably our first talk today. Heiko Wien from Bremen University, from the Institute BIBA. He's a partner in one of our projects, the EU project Epicenter, where we are looking at a Hyperloop use case, deploying a Hyperloop use case in the industrial logistics, which he will tell us a little bit more about in his talk as well. And we are happy to have him here today to tell us more about simulation and modeling of that case, involving the technologies that we've chosen there for this specific use case. Without further ado, I would say, Heiko, the floor is yours. The screen share is yours. And we can start there. And maybe Andrea could already make Bart Stubbing the second co-host for this, for the second presentation that we will come to later on. Perfect. The floor is yours, Heiko.
Thank you very much. Thank you also for the invitation for the vacuum transport seminar. I hope everybody can see my slides. Okay.
Yeah.
So you introduced already myself. My name is Heiko Wien. I'm a researcher at BIBA, which is the Bremen Institute for Production and Logistics, located at the University of Bremen. And in this term, the "at" is quite important because we are not part of the university. We are located at the university, but our directors are at the same time professors at the university. And I'm going to talk about the planning of Hyperloop-based CargoTube routes. First, I want to show you the table of contents I've prepared for today. So first, I want to motivate a little bit why to use Hyperloop and CargoTubes for transport. Then I will very shortly introduce the Epicenter project. Lucas mentioned already a very short introduction into the Hyperloop technology, because I assume that all of you know a lot more about this technology than I do. And then I will come to the main focus, which is about the planning of Hyperloop routes or CargoTube routes. I will show you the methodology and how this methodology can be supported with simulation. I will demonstrate the main results we have already achieved in the Epicenter project. And finally, I will have some discussion and conclusions. So why to deal with CargoTube? This slide shows you the Green Deal from the European Commission. I think everybody knows it. There is this green brownish part, which is the transport sector, or what the transport sector contributes to greenhouse gas emissions. And how to say, the objective is to reduce it until 2050 by 90% in relation to 2005. So, but there was another study completed by the Fraunhofer ISI called Net Zero Carbon Transport in Europe until 2050. And they came to the conclusion that this is not enough. So a Paris-compatible greenhouse gas budget for European requires zero carbon transport before 2050, and the EU is not on track for that. Assuming a linear emission reduction path, transport emissions have to be reduced by 36 to 42% from the current levels until 2030. And from that point, it should go down to zero until 2044. Then we would be on track with the objectives set in the Paris Agreement. So the conclusion from that is that we have no time to lose, and the reduction of greenhouse gas output needs to begin immediately. And within the project Epicenter, we are looking for answers to that. So epicenter stands for Enhanced Physical Internet Compatible Earth-Friendly Freight Transport Answer, and it's funded by the European Commission. So there are three big areas, I would say. So one big area is about new transport routes, which is, for instance, the Arctic and wildlife-friendly routes, or the new Silk Road. And then there are two more technology-driven topics. The first one is Hyperloop, zero carbon transport, with saving up to 80% of energy. And the other one is autonomous electric vehicles, zero carbon transport with electrified trucks. And I'm focusing in the context of this project on the Hyperloop case. So what is the map of matter? What is the problem? The problem is that we are losing a lot of energy. For instance, when trucks on interstates are running, they lose about 15 to 20% due to aerodynamics, and they lose about 58 to 59% through their engines, bringing the energy on the road. When looking at high-speed trains, the problem is even worse. So when we have a train running at 400 kilometers per hour, the energy loss is about 83% due to air fraction. So this brings up the idea of putting the trains, for instance, in an evacuated tube, which is then called Hyperloop technology. Within this evacuated tube, we are running pods. They can be pressurized or not pressurized. It depends on the cargo or what we want to transport with the pods. And we can also levitate the pods so that we have no roll friction, and we have a mechanically decoupled system. So this leads to less wear, less vibrations, and we can run the system in an automated and controlled manner. Within the mentioned epicenter project, we are also, it's more or less the University of Applied Science, Emden-Leer. They're going to set up a demonstrator with a steel tube with a length of 24 meters and a diameter of 1.7 meters. They want to have a pressure tight down to 1% of PATM, and it will be fully hooked up. So this demonstrator then we can use to do some real technical experiments with this technology. Coming to my main topic, the planning methodology. We have an example in the epicenter project where we want to connect a logistics service park, which is a logistics hub a little bit outside of a city, and connect this one with an automotive production plant. And I've researched the literature a bit about how planning works in infrastructure projects, and I came up with the German Federal Highway Act, which is a 5-phase planning design, starting with demand planning. Then we have preliminary planning, design planning, authorization planning, and finally the detailed design and construction. So in the demand planning, the planning is all about the demand we have. So in our case, that means how much cargo needs to be transported from the logistics service park to the automotive production site. The preliminary planning, it's about where can we put the logistics service parks and how can it be connected with the production plant. So we have to think about possible routes. In the design planning, we have to specify the routing more precise, and not only in 2 dimensions, but we have to think in 3 dimensions. So maybe there are things which need to be bridged or whatever. And we have to think about the capacity of the connection and is it economic viable. In the authorization planning, it's about the legal aspects we have to fulfill, and we have to make sure that the land which is used to put the route on needs to be acquired. And finally, the planning is about the implementation. So this will be more or less detailed project plans to set up and to operate the system. On the next slide, I have this example we are looking at. We have this logistics service park, which is down here at the map, and we have an industrial plant, the automotive production plant, which is in the city of Wolfsburg. Now everybody knows about what plant I'm talking. And the distance is about 12 kilometers, or between 9 and 12 kilometers. It depends how we connect it with the CargoTube. The volume we have at the moment is between 10,000 and 12,000 cubic meters per day. And when we use this box, which is shown in this picture here below, then we need around 12,000 boxes transported per day. And the first assumption is that we can design a pod which can carry 6 to 10 boxes. So this is the example. Now the areas of interest are, is it economic viable? And is the operation viable? What are the environmental impacts? What are the costs versus benefits? And what is the local acceptance of such a new transport technology? Now I'm going from step to step in the 5 phases. The first one was demand planning. We saw already that we have to transport 11,000 cubic meters per day, and the distance is between 9 and 12 kilometers. But the cargo is not arriving evenly distributed. So here I have a demand curve, a so-called demand curve, and you can see that during the night, these are the numbers of the incoming trucks. They are low. It's between 2 and 5 trucks during the night. And we have a peak around noon where we have from time to time 12 trucks per hour. So this needs to be, we have to make sure that these peaks are not a problem when we have the final solution. Concerning the preliminary planning, we were looking for locations which can host the logistics service park. And you see a map, and you see a few of these areas which have been considered. They're numbered from 52 to 59. And we had some criteria to assess how good these locations are suited to host the logistics service park. And the criteria were space requirements, the stage of development, the location, and how good is it connected to the roads for the trucks. Then is it connected to public transport system? Is this area available, and are there any other restrictions which might be important? You see above here a bar chart with the outcome of the assessment using this criteria, and you see that number 52 is the best suited. There are 2 other locations which are 56 and 57. They are also got a good number above 3, and others are not so good suited. So now the question is, how can we connect this area when we choose 52 with the plant, which is a little bit outside of this map? Within the design planning, we also have to look about the stations for the Hyperloop system. Here we have the first draft, how we think that the Hyperloop station can look at the logistics service park. So it's designed as a cross-docking station. So below here, we have the process of the incoming trucks. They have some waiting zones. Then they are unloaded, and they load some empty stuff and return. And within this area, which is called here the flexible warehouse structure, we have the cross-docking. So the goods are sorted, and they are brought to the Hyperloop station, where we have an automatic loading into the pods. And we have one tube going to the plant, and we have another tube coming from the plant, bringing back empty boxes, which are then used in the cross-docking station again. And we assume that the whole loading and unloading within this Hyperloop stations is automated, so that we can use robots to do this stuff. Okay, this is the preliminary, the first stages of the planning. But when we set up a new transport systems, there are many stakeholders involved, and there are many questions connected with switching to a new and innovative transport technologies. Examples are, what are the building costs and what are the operating costs and what are the benefits or savings we have, and when can we reach the break-even points when we do such a big investment? What are the positive impacts concerning greenhouse gas emissions? And are there other positive impacts, for instance, concerning particle matters or noise? Is the logistics operations reliable in terms of timeliness and throughput? What are the socio-economic impacts, for instance, the employment or the regional prosperity? And finally, what freight network configurations can be the best? So there is no one simulation tool which could answer all these questions at the same time. So that we made, also within the Epicenter project, we made a framework to assess transportation technologies. And we have divided this framework into impact design, the domains, which are socioeconomic impacts, climate-related impacts, microeconomic impacts, and logistics operation-related impacts. And we have different simulation approaches mapped onto these domains, which are discrete event simulation, system dynamics, cross-impact analysis, life cycle performance assessment, synchro model optimization, and a special tool from Einride they are producing in these electrical pods, which is called the Einride electrification analysis tool. For each of these simulation approaches, we have collected tools to be used. They come either from partners within the Epicenter consortium, or they are freely available, so that we have a set of tools where we don't have to pay fees for. From these simulation tools, we can generate data, simulation results, which we then can use to calculate key performance indicators, which we define for the economic, social, or environmental domain. So this is our framework. But before we can use a simulation tool, we need a lot of input data. And we struggled a little bit in collecting all this input data at the beginning, because we saw that there are some constraints we have to take into account, and others can be calculated by more or less simple formulas. And so we set up a spreadsheet to calculate this basic data. And you see here on the right side a part of the spreadsheet, which is concerning the Hyperloop layout. We have 3 columns. One column is giving the unit. Then we have a column where we have to enter our input values. And then the green fields, these are the fields which are calculated by the spreadsheet. And within this area, the Hyperloop layout, we can, by specifying that we have 2 tubes, and the length of the tubes and what diameter the tubes need and so on, we can calculate the amount of steel we need. Then we can further calculate the amount of concrete when we want to have a concrete floor within the tube, and also calculate the amount of steel we need for rails and so on. That depends on the design decisions, but when we have the design decisions, we can update the numbers within the spreadsheet, and the numbers are calculated automatically. This spreadsheet is quite large, and it covers the following areas. It's first, there is a collection of constraints. Then we have the Hyperloop layout. We have physical properties like acceleration, the time to evacuate the tube or the tubes. Then we have the pod layout, the bay layout. The bays are located at the stations, at the endpoints of the Hyperloop. We have the operational properties, and we have costs for building and operations. So now when we have the basic data, first some results from the spreadsheet. Around 12,600 boxes must be transported each day. We have a CargoTube system, which is expected to have 2 tubes of the length of 12 kilometers and 1 tube for each direction. Then the minimal inner diameter of the tube needs to be 1.65 meters. This is a constraint from the boxes we want to use. And this results in 14,000 tons of steel for the tubes and 20,000 tons of concrete when the floor inside the tube is made of concrete, and further steel and concrete is needed for the pillars and for the rail systems. Then the total volume within these two tubes is around 45,000 cubic meters. And when we have two pumps, the evacuation time down to 10 millibar is around 3 days, which seems to be quite long. Assuming a repressure time and automated unloading and loading time of 1 minute each results in a handling time of 4.2 minutes in a bay, including the evacuation. So when a port is in a bay, the process is that it is repressured, then we have the unloading and the loading, and then we have the evacuation. And this takes 4.2 minutes. The total travel time for a pod is 5.5 minutes, where we assume an acceleration of 0.1 g and a cruising speed of 150 kilometers per hour. And we also include the time for braking. In full operation, this system can handle 36 pods simultaneously. So this is what we can calculate from the spreadsheet. But we also use discrete event simulation to check these numbers. And you see in the middle of this diagram, you see the two tubes, one from the LSP, which is on the left side to the manufacturing side, and one tube which is going back. And on each side, we have 6 bays, and the process in each of these bays is what I said before. So in the beginning, you have to wait with the pod until the bay is free. Then the repressuring takes place, the unloading and loading, and then the evacuation again. And then the pod has to wait until the tube is free, and we assume that there is a safety distance of 1,000 meters. So when the last pod is already 1,000 meters in the tube, then we can send the next one. We can also define some performance indicators, which we have here on the right. Here is, for instance, the boxes to transport. This is the kind of backlog we have to transport. Then the tube usage, how many pods are in the tube at a specific point of time, and the bay utilization. So how many bays on each side are utilized for one moment. We can run the system and can do some experiments, for instance, with specific demand curves during the day, or we can also experiment with the number of bays which are open. And I also have some results from the simulations. The whole system is capable of transporting more than 16,000 boxes from the LSP to the production plants when all 6 bays are running, and there are no waiting times. So that means that the cargo is coming evenly distributed, and then there are no gaps in providing cargo which is transported to the production site. The maximum number of pods in the system when it's fully loaded is 33, and this is a difference compared to that what we calculated with the spreadsheet. There we had the number of 36. Then with only 5 bays in operation on each side, the system is still capable of transporting more than 13,500 boxes. When we use 4 bays, then we can still transport 10,500 boxes. So 4 bays is the minimum, but then nothing should break, otherwise we have a problem. So it's better to have 5 or 6 bays and to switch them on and off when needed. With the demand curve, as we have seen in the beginning from the demand planning phase, there are a few waiting times or nodes which do not last longer than 60 minutes. So we can transport all the cargo, but at some points in time, the cargo needs to wait a little bit until it can be transported because the backlog is growing. So coming to discussion and conclusions, there are many advantages using a CargoTube system. So the major advantage is the reduction of greenhouse gas emissions to zero. It depends, of course, on the electricity, how it is produced. Noise, weather exposure, and total energy consumption will be substantially reduced. And we have reduced energy storage requirements due to electric propulsion and continuous recharging in the operation of the enclosed system. The CargoTube design is reliable and flexible, while automation reduces costs and personnel requirements. This is also important, at least for Germany, because we have a lack of truck drivers. And so this will help to overcome this situation. And we have a significant reduction in road traffic and congestions, especially in urban and densely populated areas. But there are also some disadvantages. The first one I mentioned already is the time we need to evacuate the tubes. At the moment, there are 3 days, but we are thinking, or it needs to be proven that the port traffic can start earlier with reduced speed, for instance, while the tubes are not fully evacuated. That could reduce the time. We can also reduce the time by employing more pumps. So this is the point we are still in discussion. And that's from my side. Thank you for your attention, and I'm open for questions.
Thank you very much, Heiko. Thank you for the great presentation. And I think Daniel is going to take the questions, right?
Yes, so thank you, Lucas. Thank you, Heiko, for the nice talk. We would then take the chance to jump directly into the questions. There have been some of them are quite interesting ones. So the first one is more regarding the approach Heiko you took to realize this model, and it would be what added value has this proposed cargo use case compared to the ones we have been seeing currently from other Hyperloop players when designing such a cargo use case?
I don't know the other one, so it's
for example, in a European level, when I think we have been seeing also some of them from Hart, also from EuroTube at a certain point. Okay. Let's say what is the characteristic or what is different, let's say, from these type of approaches now, the one conducted from you?
I don't know, but I think what we are doing here, maybe Lucas, you can jump in. But what we are doing here is a very specific solution. We are transporting cargo from one point to the other, so we don't need such big tubes concerning the diameter of the tubes, and we can design it very specifically to the demand we have.
Yeah, and it's a specific logistics warehouse situation, I guess, where the implementation would be quite quickly compared to any other project or use case that we've seen before. There's a lot of established technologies used as well, and the project partners are quite keen on having a solution for the problem, and it's a specific area with just a 10-kilometer demonstrator tube, so a lot of Hyperloop technologies could probably be tested very, very quickly if the decision comes to build such a connection.
So it's basically a solution which adapts to a region and to the needs of a certain route. It's basically a tailor-made approach for each.
Yeah, exactly. A tailor-made approach that doesn't necessarily have to fit into a bigger network, where Hyperloop promoters can really test the technology and go deep into some of those technologies and automations to see if that works in a Hyperloop further on.
Okay, I see. Mm-hmm. Thank you for that. Then we would have more questions now from on a technical side. Someone is asking, what kind of vacuum pumps are you assuming to get 3 days of pump down? And does this 3 days fits the requirement of the system?
Hey, Lucas, probably you know more about that. I do.
Yeah, I think we did all that in a big discussion with all the other parties involved. So the question was, do you use pumps that can quickly pump down the 10 kilometers, or do you use pumps that would afterwards be used to just sustain the vacuum? And the case is that it's better to just invest in pumps that you can use to sustain the vacuum. And if you need to do maintenance or so, cut off a small part of the tube if needed. Well, this is not such a long tube. So in other cases in sanitization, we've seen every 10 kilometers, the tubes can be split to evacuate one part, but then you would have much more vacuum pumps for the other parts as well. So in this use case, you would probably rather have a few more pumps employed at the very beginning, and then you just need the pumps that sustain the vacuum, and therefore those to sustain the vacuum would take quite long to evacuate such a big tube, of course. But of course, you could mount an infinite number that you want at the beginning to just pump down at the very first time.
Yeah, because yes.
For this simulation or for calculating the basic data, we have assumed that we have two pumps, and the type are Bush R5. They have a flow at inlet of 1,400 cubic meters per hour, and they consume 30 kilowatts. So this is what we have used in the Excel spreadsheet as a starting point. Of course, we can enhance the number of pumps, or we can use other pumps with other data, and then the numbers will change.
Okay, yeah, because this is then directly linked with the next question. Someone asking that if isolation valves have been taken into consideration for the pumping time, since having the possibility of cutting the flow between two segments, you also would then maintain the vacuum as soon as you close the gate. Has this been taken into account maybe as an option to reduce the vacuuming time once you open the door for a vehicle or a cargo pallet to enter the system?
I would say there's different technologies again. I think this is the worst case we assumed, Heiko, right? That's the biggest vacuum chamber we've probably assumed there, with just a big chamber that needs to be pumped down, not fit to the vehicle, or any kind of interesting or new technologies with respect to vacuum pumps that could, for example, look at side loading and a combined tube track airlock. That's nothing that's assumed here. That would basically cut the pump downtime pretty much to zero if you've used some of those technologies. But we've assumed the worst case here, I guess, in this first version.
Okay. Then there is another question related to the throughput. The question is, can the throughput be adjusted depending on the demand? This is something which has been taken into consideration.
Yes. Of course, the numbers I presented are the maximum throughput. Yeah. Of course, you can, when the demand goes down, when we have a specific demand curve where during the night less trucks are arriving, and during midday we have more trucks, then we can during the night we can close some bays, and it's still working with the throughput we need. Of course, we can also design the simulation model to have more than the 6 bays. Then we can maybe have a bigger throughput. But I think at some specific point, then we need another tube, because then the tubes are the bottleneck.
And again, I think in our discussions we've calculated with the worst possible safety distance, and so I think there's room for a few more pots, but still, that's the worst case you can assume for the use case.
And it's quite conservative. That's good to know.
Yeah, better be conservative than to overshoot.
Excellent. Then I would say we answered the very last question before we move on to the next talk. Someone from the audience is asking why 150 kilometers per hour and not faster? What have been then the metrics there for this value, and if it would be possible to publicly share the simulations to have a deeper look in them.
Yeah, again, this was a conservative approach at the beginning, and we can set up the speed a little bit. This is the simulation model is designed in such a way that you have a tableau where you enter such values. What will be, or what is the cruising speed you want to have, and so on. Of course, this also has an impact on the acceleration and on the braking.
Exactly,
There is at this short distance, 12 kilometers, it probably makes no sense to go to hundreds of kilometers per hour.
You can afford yourself higher accelerations probably than with passengers.
Yeah, of course.
Excellent. Then I see we have a few questions, but probably it would make sense to move on to the next talk, also to keep exactly the time for the next speaker. I hand over to you, Lucas, again. Thank you very much, Heiko, for your talk.
Thank you.
Thank you very much. Okay, so our next speaker is Edward Stubbing. I hope I'm pronouncing that the right way. He's a department manager at ITS and Emerging Transportation Technologies at AECOM. And I've been very happy about the support that AECOM has been given to the Hyperloop community already that we've seen from you. I've also met Walter Perry from your Dutch department at the European Hyperloop Week last year. It was great fun working with them together, seeing you guys also publish studies about Hyperloop there. Just a little bit of background information about yourself. You've got a Master of Science in Transportation and Urban Systems and Transportation Planning and Management from the University of Westminster and North Dakota State University. And you've been working in quite a few positions right now at AECOM, researching all kinds of mobility-related projects. So we are happy to have you here with your expertise and talking about the study that you've done about Hyperloop to look at that. Thank you much for being here, and I would say the stage is yours.
Thank you, Lucas. Very nice to be here, and much appreciate the invite. So I'm going to present a little bit more high level, I think, than Heiko just did, taking you back a few steps and looking at the system at a wider level. And I'll skip over this. I think the focus of my talk is going to be on a paper that was commissioned by Transport Canada for looking at the feasibility of Hyperloop system. At the time, it was specifically looking at passengers, although it did recognize that there was an opportunity for cargo as well. And it sought to address two real questions. It sought to understand, whether Hyperloop was ready to be deployed, and if it was, what the impacts would be. And then secondly, to look at it directly in comparison to high-speed rail and maglev technologies, which were the two other options that certainly in North America, I'm based in Canada, just for reference, that certainly in North America are being considered for high-speed ground-based transportation corridors presently. So the study was structured in such a way that it had several key components. I'm not going to go into all of them because we'll be here for 5 hours, but it's a great report, so please feel free to read it. It is publicly available. I'm going to pick on the pieces that I think are probably more interested to this group. So I'm skipping over the literature review, jumping straight into the technical features. We did a technology readiness assessment, or a TLR approach, to looking at each of the components to the system. And that was really important because it starts to highlight what's ready, what's maybe not, and then leads into the second piece, which I'm going to talk about, which is where we did a risk and a hazard assessment. And the risk and the hazard assessment is really key for Transportation Canada as a regulatory body, because what they're sitting there doing is they're going, right, what are the risks? What do we need to legislate? What do we need to regulate? And what do we need to do to make sure that not only riders and users of the system are going to be safe and comfortable in this, but also the surrounding communities that this system is going to pass through. So I'm going to talk through a number of different things that we did in terms of looking at risks and hazard. But I think firstly, I wanted to just touch on some of the technology that we looked at. So we looked at a number of different areas. We looked at the infrastructure, so the tube and the structure. We looked at the propulsion and the power delivery, whether it was onboard or infrastructure side, levitation and guidance, system topologies, Some of the configurations, we did do a 500-kilometer test system and looked at some of the impacts that would happen as a result of going linear versus infrastructure side, and some of the other combinations that we could look at. And then we also looked at it from an environmental lens in terms of, in North America, there's an environmental assessment process for any technology or transportation system that is implemented. And so we looked at some of the impacts that the Hyperloop system could have from that side. So looking at noise, environmental concerns, heritage, archaeology, etc. To make sure that this study was as good as it could be, we engaged with a number of the technology developers, your Virgin Hyperloop One, Transpod, Zeleros, and I think there was about 10 in total that we conducted interviews with. And we used that information to run some modeling to look at the level of technology readiness. And so our results are based on a combination of the questionnaire responses, the Python model that we developed, and also our independent review of the technology as well. And we used the NASA TRL system, which for those of you that maybe have seen this before, it effectively gives 9 levels of readiness. So everything from, that's a great idea and it's in somebody's head, to that's been implemented and it works and we trust it. And so what we did is we assessed these various technologies, and we looked at a number of different components, and we came up with a lot of questions. And you'll see in the bottom right, that there's some things that are not that far away from being ready, like the levitation and the guidance system, like the vacuum and the power. And then there's things like high-speed switching, which is, still quite in its infancy and still has a lot of uncertainty. And obviously, as we were listening to Heiko's discussion, he's talking about 6 bays. Well, are those bays all going to be at low speeds like you would see currently with high-speed rail and maglev, where, you're talking 80, 90 kilometers an hour at most that those transfers can happen? Or are these going to be in the hundreds of kilometers like the system is projected to travel at? So it came up with these ratings. And from that, we had a number of unknowns. And I think that's fair of a technology at this level to have these unknowns and to leave a lot of questions that still need to be answered. What is acceleration going to be? Some of our developers were saying, we can accelerate at 3, 4, 5 Gs. And it's like, well, what's the impact of that on a human body? Is that even feasible? What emergency procedures are going to be? You just heard about what happens if pressure is lost in one of the sections of the tube. Do you close off the section? Do you close the whole entire system? How will boarding and alighting work? Some people say the pod's going to come out of the system. You're going to board and it's going to be reloaded and pressurized before being sent off. Others think it might be a loop, a bit like a train station. You come in, you board, and the loop continues on. And then obviously we talked about the environmental impacts as well. What is the noise impact? What is the vibration impact? What is the visual impact to urban areas? One of the things that we looked at was tunneling versus above ground of the tube system, and what that means for land value, what that means for structures placed above a tube. That is potentially having capsules or pods traveling at 1,000 kilometers an hour. What does that mean in terms of the impact of the land above it? So we had a lot of questions that still need to be answered. And I would say, to be fair, this report was published in 2020. Many of these still need to be answered. And we also recognize that there needs to be a certification system that needs to be implemented. And that's going to be something that, with a technology like this, many different countries are going to want to have their own certification facilities. That can be quite challenging. That can be quite costly. Who's going to bear that cost? And so maybe there's room for collaboration there. And I think if you look at the news recently, that you're starting to see some of the certification, it's starting to be considered as an important next step. So jumping into the next phase, as I say, we sort of recognize where the technology is at, where we think it could go, what the application could be, talking about it as a passenger transportation mode, and therefore start asking the questions around what are the hazards, what are the threats, what are the risks that come with this. We know what some of the trip types, we know that why it's been promoted as an important mode, why it's been given a lot of encouragement to be a better mode than existing high-speed rail or potentially maglev. What is the experience going to be like? I think many of us probably have stepped inside a conceptual Hyperloop pod and seen this beautiful futuristic environment that we all get excited to ride in. But if we're going to be accelerating at 1, 2, 3 Gs, where's the safety in those seats? What's the rules going to be about whether you can get up during travel to use the facilities? What if suddenly emergency braking has to happen at 1,000 kilometers an hour and you're not strapped into your seat? So these sorts of questions start to arise when you think about the experience. One of the biggest unknowns, I think, is the terminals. Lovely picture here of a potential terminal, but what does, that's showing that there's a single track where capsules are going to load and unload. Is that realistic? What's security going to be look like? We've obviously all, I assume we've all flown. We know what the security procedures are like when you go on a flight. Is it going to be the same for Hyperloop? Or is it going to be like a modern railway station where there's very little security? You can walk right up to the vessel or the carriage and board with minimal security, very last minute. That's certainly what a lot of the developers think. But if you talk to regulators, they're saying, no, you're going to have screening. You're going to have potentially identification verification. What does that mean for the amount of time and this footprint of these terminals? So moving into our assessment approach, we utilized a two-part approach to assessing various different hazards. The level of severity, i.e. what is the impact of this if it does happen, and then also the likelihood of it happening. And so that gave us a scoring process for all these various different hazards and considerations. I will share this slide deck afterwards, so there's a lot of text to go through. So we looked at a number of different areas. We looked at the Hyperloop capsule, the pods. We identified factors like what happens if there's a pressure imbalance? What happens if there's a technical failure of the life support system? What happens if the low-speed wheels do not deploy as the pod is approaching or departing from a terminal? And we recognize that there's a number of risks here. We recognize that there's also risks if the door of the pod doesn't open or close. What happens then? And so we categorized these risks and started to realize, right, there's risks out there that are, if they happen, they're critical, and the probability of them happening is medium. And so therefore, that's the sort of thing that starts making regulators go, this is something we might need to regulate. This is something we might need to bring legislation in to manage and protect. Skipping through to power, we had questions like, what happens if there's a temporary power spike and some of the guidance or the levitation is impacted? What happens if the magnetic gap between the primary and secondary motor fluctuates during operation? What's the impact of this? What happens if the entire propulsion system cuts out? And that starts to lead into, well, what happens if the power goes out? What's the evacuation procedures? What's the backup systems? How are we legislating for backup systems into these pods? And we start to realize, okay, well, we've got a pod that's been developed. It's going to take 16 people. It's going to have an onboard battery, and it's going to weigh this. And this is therefore its capability of accelerating. Then you start bringing regulations. Well, now you need to have a reserve power system. Now you need to have a backup oxygen system. And suddenly the weight of your pod increases, your size of your pod increases, or you have less people sitting in the pod. What does that do to the economics of each pod? So you start realizing how regulation and legislation can have a huge impact on this system. Looking at the corridor and the tube infrastructure, what happens if you have an above ground system and the pillars fail? What happens if trees fall on the tube? What is the process for monitoring and the maintenance? What happens if the high-speed switches fail? These sorts of questions start to appear, and you realize this is going to have some operational impacts. I'm flying through these because there's a lot and it's a bit of repetitive, and I really want to get to the questions because I think that's where the excitement is. Communications. This is one of the areas where actually from a technology readiness level point of view, it's quite well advanced. There are a couple of queries though about the capability of existing communication, even 5G communication, being able to match the times and the requirements of a system that's traveling over 1,000 kilometers an hour. And so this is where you start to see some real risks. Probability of them happening fairly low, but the risk if they do happen is quite high. What happens if you're talking about headways, and the communication system between each pod fails? We heard Heiko talking about 1,000 meters. Some of these developers have said they think the headways could be a matter of seconds between these pods. What happens if pods traveling at 1,000 kilometers an hour, seconds apart, need to communicate constantly? What happens if that communication fails? So you start realizing, okay, now a regulator might start saying, well, actually headway has to be 4 times the braking distance of each pod, and you need to have some redundancy system. That means if one pod fails, every pod immediately brakes. There's a lot of complexities that go into implementing those additional systems. Terminals, I think, I touched on the security and the safety side of things. We did talk a little bit about the exit and entry. What is the footprint going to look like? What is the mechanics and the security around this going to be? One of the big concerns from any regulation body when you start talking about pressurization or high speed is the risk of terrorism and threat. And that comes with that. And that's something I'll pick up on in one of the subsequent slides. From a maintenance point of view, start to look at what happens if vehicles are damaged during storage and maintenance. What's the procedure in terms of an inspection? You think about the airline industry right now. Before a plane takes off, an inspection has to be done by the captain. What does that do to the delay in terms of the turnaround time for that pod? If you're saying now every pod has to be visually inspected or has to go through some sort of diagnostic system in between each trip, suddenly your turnaround time isn't minutes. It could be 30 minutes, 40 minutes, 45 minutes, depends what the regulator requires in terms of the inspections to be done before the trip. And then operations and maintenance, what happens if pods stall in the system? What happens if they stall at the station? What's your procedures? What do you have in place in terms of removing pods from the system? What do you have in terms of there's something external that collides with part of the infrastructure corridor? You might have tubes that go over a highway. What happens if a truck veers off that highway and hits the pillar that supports those tubes? What are your procedures for inspecting and resuming operations along that corridor? I mentioned we also looked at a threat and vulnerability assessment. So this is where you start looking at what are some of the emergency conditions that could happen. And this is where you're really looking to look at security, vulnerabilities, and what the causes are. So for example, one of the ones that comes up a lot is what happens if a passenger has a medical emergency while they're on a pod? What are the procedures in terms of stopping that pod? Is there a member of staff on the pod who can activate an alarm and cause a stop? Does it rely on the other passengers alerting somebody in a remote location that there's an incident that's occurred? What happens if oxygen leaks or there's no oxygen in the pod and everybody passes out? What's the procedure for that? So we start to see that there's a number of other threats and vulnerabilities where traditionally, as we've seen in the airline industry, as we've seen in the rail industry, regulation and governance have to step in. So what we realized, and I'll make this the last slide because I know we're up against the time, is that there are 6 different areas of policy that we think that in this case, Transport Canada, but really any governing agency needs to look at. They need to look at vehicle design. They need to look at regulating infrastructure, regulating the system component, regulating the communication, determine how to regulate environmental factors, and then what regulations are for security. And you can see on this slide that below each of those 6, we've tried to identify some of the items we've flagged and where they might sit in terms of regulation. And you start to see that actually something like energy is probably going to be regulated by a number of different sectors. Why does this matter? Because these 6 policy areas probably sit with different teams in a regulatory body. And so we wanted to highlight to Transport Canada, this is going to be an interdepartmental effort to develop standards for this. This isn't just sitting with one team as it currently sits. And so we created this lovely issues map, which will be shared. It is in good resolution, so you can see it, you can zoom in. Something that I think is a really cool summary of everything that we've talked about. And then key findings, as I mentioned, we've realized that there are a lot of factors that need regulation, that need legislation, that are going to impede the commercial viability of this system and the development and the operation of the system. And so these are things that really need to be worked on by regulators right now to help the developers identify how to prepare for these, rather than letting the developers develop a beautiful system and then throwing these regulations on them. And I'll stop there. Thank you.
Thank you very much, Edward, for the very nice presentation. I also see we have some questions from the audience. The first one would be, how would you assess the research and development that is currently going on to adjust the TRL level from a few years ago, where would you suggest new research to be started?
Yeah, it's a great question. So one of the recommendations we have for Transport Canada when we submitted this in 2020 was to say, in 5 years' time, in 2025, you need to do an update to this because of the rate of development of the technology. You know, we all point to Musk's paper back in 2013 as the birth of Hyperloop, and here we are in 2025. 5 years, that's a long time in a a technology that's only been alive for 7 years, according to Mr. Musk. And so we recognized that you needed to do an update. You definitely needed to involve the developers because of the commercial sensitivity of what they're developing. Without them, you can't do this assessment. And so I think that's the key, is getting developer buy-in to doing that assessment.
Yeah, that makes completely sense. This is also then linked to the second question. As you referred, the influence of regulation on the technological development, what would be regulation that you would want to see as soon as possible?
So I think one of the things that a lot of the developers are doing at the moment, and they're still doing, is looking at their pod design. And so regulation around what needs to be in the pod for the passenger and what rules apply to the passenger are going to affect pod design significantly. I think if you start talking about communication redundancy, you could probably do that on the infrastructure side. So it's not such a critical feature to the design, but knowing exactly what you have to have in your pod, and therefore the space that you have left or the capacity you have left for passengers is really important to feeding into the pod design, but also subsequently the commercial viability of the passenger pod you're proposing.
Okay, that's quite interesting, because I would have thought of the interface to the track, because you may have a different train or a pod, but the diameter and the track has to be the same, meaning also the propulsion. That's and
apologies, because I'm not as familiar with the European model, but I know that there's been talk of a network where you'd have different pods operating on the same network, and therefore that would be more important. In North America, definitely the thinking is that each developer is going to have their own track. So yeah, you're right. If you were going to go down multiple different developed pods on the same track, you would be quite right to say that that's more important.
So the US, that's not, let's say, the main concern for. Okay.
Correct.
Okay.
Yeah.
Great. Then the next question would be, will regulation just mark certain high-level safety criteria, or will there be specific requirements, as you said, like the headway?
Yeah, so that's a really good question. We in the report we talked about the aviation industry and how they set up runway takeoff and landing spacing. That is left to an individual airport based on the design of their runway, and there are guidance, but there's not a set headway for landing and departures at an airport. Our recommendation was that that's likely going to be the same for the Hyperloop system. It's going to be a mixture of, we have recommendations, but we're not going to tell you that it has to be this, because it may depend on the operating speed, it may depend on the acceleration speeds. What we do point to is that there will need to be a lot of testing on what human tolerance can handle in terms of the G-force for acceleration, and that will probably dictate.
Yeah, this makes a lot of sense. Excellent. Thank you for the reply. The next question would be, have you separated the analysis into risks that apply to the passenger and risks that apply to the communities, people nearby? If this is of interest to potential freight applications, because generally only the latter group would be applicable.
So in one of our findings was that there are a lot of unknowns about what the wider impacts of the system are going to be on the communities they go through. In North America, as I mentioned, we have an environmental assessment process that any infrastructure development has to go through. One of the subsequent studies that Transport Canada should commission when the technology is a little bit more defined is an assessment of the application of this technology to those existing environmental standards, and whether the environmental standards and process that they have is an effective tool to measure and then subsequently recommend mitigations to the Hyperloop technology.
Okay, thank you very much. And then someone is asking if it would be possible to share the report. Is there a way of accessing?
Yeah, the report is public. It is shared by Transport Canada. I will then make sure there's a link included with the slides as well, which can also be shared.
That's excellent. Thank you very much. Then with this said, I hand over back to you, Andrea. Thank you very much, Edward, for the nice talk.
Yeah, thank you, Daniel, and thanks to the two talkers today for the very interesting presentation. And also thanks everyone for joining, and thank you for the participation with your questions. And I want to thank, in the name of Swissloop, EuroTube, the Institution of Hyperloop Technology, Hochschule Emden Lehr, and TUM Hyperloop. And for next week, we already have 2 talks again. So on the 22nd of May, we will have 2 speakers. The first one is gonna be Mekteb Basu from the University of Edinburgh. And the talk will be about cooling of the limb on the infrastructure side, and also a cooling concept for a launcher. And the second talk will be from Federico Lucema, which is a propulsion engineer at Celeros Hyperloop. And he will talk about the design and optimization of a virtual prototype for a ground transportation system. So we will have 2 very interesting talks next week. And with that, I wish you a good evening and hope to see you next week. Thank you, everyone.